Well, so far we've talked about a rather modest degree of fractionation. We had a full experiment in 32 runs. We just ran half of it, 16 runs. But actually, industrial experiments can be run at very much higher degrees of fractionation. And I'm going to be talking now about a 1/16th fraction of a 2 to the 8th. You can see in here, this is an experiment done with a molding operation, and the thing that was we were concerned with was the shrinkage of the piece, and some of the factors, there were 8 factors which were thought to possibly affect that: mold temperature, moisture content, holding pressure, cavity thickness, booster pressure, cycle time, gate size, and screw speed. So they're all things that might have an effect. And if we ran a full factorial design in all those 8 factors, that would be 2 to the 8, which would be 256 runs. So we didn't do that. We ran just these 16 runs, and these 16 runs are chosen again rather craftily, and it actually involves some neat mathematics, but we don't need to be involved in all that. Most people would much prefer to simply use this little book which you're getting with this package, which is Practical Aid to Experimenters by Soren Bisgaard, which shows a list of all these designs that you can use. And so anyway, this is one of those designs, and it has an interesting property. You can see that the main effects are not confounded, not mixed up, not aliased with any 2-factor interactions, and we're not ignoring 3 and higher. The 2-factor interactions actually go in groups, so that you have the 1, 2, 3, 7, 4, 8, 5, 6, for example, going together. And so that minus 0.6, if it was real, probably is just noise, but if it was real, it could be due to any one of those things. Fortunately, there are ways of having run a design like this. If you get one of those sets, which is rather large, so you can see that 4.6 there corresponding to 1, 5, 2, 6, 3, 6, and 4, 7. That is a rather big one, and you might want to look at that. And you want to look at it, there are ways of adding a few more runs. That's discussed in BH squared, box 100 and 100. Ways of adding a few more runs, which will sort that problem out. So anyway, let's just look at what we do and what we get if we plot these again on normal probability paper. This part here probably looks like noise. Factor number 3 is holding pressure. That's coming up. Factor number 5 is booster pressure, so those seem pretty definite. This is one of those strings of interactions, and actually we did run some additional runs, and we found out that the important interaction is 3, 8. So it looks as if factors 3, 5, and 8, that's holding pressure, booster pressure, and screw speed, are the important factors. And again, you see, there's 2 aspects to this. There's 5 factors that are in there for the ride. That's important information. They're really not doing very much. And as I said before, to know that something isn't important is very important. But what about the ones that are doing something? Well, we can look at those again on a cube, and because if you think about it, it could have been any three factors which turned out to be important, and there's 56 ways of choosing 3 things out of 8. So it's an interesting fact that this design has the remarkable property that whichever 3 it should turn out to be, you would have a complete cube repeated twice over in those particular 3. And here you can see it's the same set of results. Of course, we just rearrange them at the corners of this cube. And when you look at that cube, it makes it very easy to see what's going on. In fact, it makes it very easy to see what this interaction is between 3 and 8. You can see that holding pressure, which is factor number 3, doesn't have much effect at low screw speed, which is factor number 8, but increases shrinkage at high screw speed. So that's what that interaction means. This book, Practical Aid to Experimenters, provides a very valuable table of designs, something that helps you find your way around in it a little easier, is these ideas of fractionation and resolution. So let me talk about those ideas. First of all, fractionation. Well, that first design we ran, the full factorial would have been a 2 to the 5th, wasn't it? Remember that? And we actually only ran a half of it. So we ran a half of a 2 to the 5th. And that, so one way of characterizing that is to say it's a 2 to the 5 minus 1, because this is like 1 over the first power of 2, or if you like, it's 2 to the minus 1. And the other design, well, that was for 8 factors, if you remember, so it was, the full design would have been a 2 to the 8th. We only ran a 16th of it, right? A 16th of it, well, what is that? That's 1 over 2 to the 4th of it, right? 1 over 2 to the 4th of the 2 to the 8th. And so what that is a 2 to the 8 minus 4. So this is really, you see, this characterization, the 2 to the 5 minus 1, the 2 to the 8 minus 4, is a nice characterization of these designs, because this 5 here is telling you that there are 5 factors, and the minus 1 here is telling you that it's a half fraction of a 5-factor design. And 2 to the 5 minus 1 is 2 to the 4, and that's telling you there are 16 runs there. Similarly with this one, this is saying there are 8 factors. It's a 1/16th replicate, because 2 to the 4th is 16. And how many runs are there? Well, 8 minus 4 is 4. And so there's 2 to the 4th runs, which is 16. That notation due to Cuthbert Daniel is a very nice way of thinking about these designs. Another aspect of the designs which I want to talk about is their resolution. Now, if you look at those alias patterns, we had 2 examples. We had that, first of all, we had that half fraction of a 2 to the 5th. And I put up those aliases there, and I said that probably the 3 and 4 factor interactions didn't matter too much. But nevertheless, let's look at them again. You've got a main effect, that's something involving one number, and a 4-factor interaction, which are aliased. You've got a 2-factor interaction and a 3-factor interaction, which are aliased. Okay, 1 plus 4 is equal to 5, 2 plus 3 is equal to 5. That's called a design of resolution 5. We've got rather a lot of ordinary numbers around, so I use a Roman numeral here for this 5 to indicate the resolution. Let's try now the 2 to the 8 minus 4, that other design. Now you can see there that the main effects are all shown as clear, but we've decided there to ignore 3-factor interactions, and really those main effects are aliased with 3-factor interactions. And so 1 with 3, and then the 2-factor interactions you can see are aliased together, so 2 with 2. So this is a design of resolution 4. And so we put on here a 4 to indicate that's a design of resolution 4. This idea of resolution is quite a useful idea. It roughly is used in the same way that resolution is used, say, in thinking about a microscope. When you get a high resolution, you can see more things, so to speak, and you've got a clearer view than if you've got low resolution. So what you'll find is that only moderately fractionated designs, like this one, for example, have a higher resolution than this one, which is a much more highly fractionated design. So what is the summary of what I've been saying? Well, as the number of factors increases, a full factorial experiment requires a very large and really unrealistic number of runs, and fractional factorials can then be used for screening designs to find the important factors.